In my previous video, we made this, the full scroll dial. It's a wireless, high-resolution scrolling device, and I've been using it pretty much daily for months now. It lets me fly through my video editing timelines and stop precisely where I mean to. I can smoothly scroll within these tiny windows, which would normally jump all over the place using a normal scroll wheel. And of course, it's super handy for my favorite pastime, reading datasheets. In this video, we're gonna make some minor changes. But hold your horses. Let's start with something easy, like the PCB, because this connector isn't quite right. Rechargeable lithium batteries usually have thermistors in them. That's the guy we're talking about. So we need a connector with 3 pins, and this one only has 2, so it's gotta go. We'll swap it out with our new 3-legged friend. The board has a missing pad, but it's nothing a little grinding can't fix. I used 0.1mm enameled wire to connect the thermistor, and used some tape to stop the wire from flapping in the wind. Here's the completed hack. Charging should now stop when the thermistor gets too hot or too cold. So let's give it a try. I'm expecting the charging LED to go off when it hits 50 degrees or so. But that didn't work. Let's try again. Still nothing. Let's just keep going. It's not like a little heat ever hurt anyone. Alright, we are nearly at 100 degrees, so I think it's safe to conclude that something isn't right. Turns out, I'm the thing that isn't right, because the datasheet clearly says the LED will remain on during a temperature fault. So let's try again with a USB tester. The current falls to 0 as expected. Nice. We can actually also tell when the charging starts or stops using just the thermal camera, if you know where to look. The eagle eyes among us would have already noticed this happening before. While we're on the topic of batteries, I also made some changes in firmware to reduce the power consumption. The power profiler shows the device automatically entering low power modes. To cut to the chase, the dial can now do something like 300 days of standby battery life by my estimate. In fact, it's so good, I haven't had to charge my dial after several months of regular use. I've also made it possible to cycle through a few sensitivity settings using the button. The LED flashes indicate the sensitivity setting, and a long press inverts the scroll direction, which is indicated by the color of the LED. This could be useful for macOS users and people who are upside down. By the way, I'm not saying we need it, but we can actually do a lot more with the one button. Just look at Enduro 2. This is for controlling a flashlight, in case you couldn't tell. Let's stay on macOS for a second. Thanks to a couple of comments, I found the pixel scrolling mode in the Linear Mouse app to really help. But there seems to be a scrolling speed limit. We can scroll faster using the line scrolling mode, but scrolling resolution suffers. Overall, macOS compatibility still isn't quite there. Linux, on the other hand, seems to support high-resolution scrolling natively. At least the lib input debugging tool does. But high-resolution scrolling doesn't work with any other apps, even though we can see the high-resolution scrolling events. If you can help with any of these compatibility issues, please get in touch. By the way, if you want one of these dials, join me over at Patreon. It's totally free, and that's where I'll be posting small updates. Okay, back to the PCBs. The hacked board works, so I had new boards made by PCBWay. I also snuck in a couple of minor changes. See if you can spot them. Now let's talk about the bearings for a minute. In my previous video, these ceramic bearings were the best, but some people weren't convinced. Thing is, they're right. Thrust bearings are better at axial loads than deep groove ball bearings. But did you know thrust bearings come in 3 separate pieces? That means they can handle absolutely no radial load.
0, is it not? No trust.
Overall, a deep groove ball bearing is simpler and already does a fantastic job. What isn't fantastic is the screw up. It actually takes 9 screws to be exact. I don't think we really need 3 screws just to capture the bearing, and 3 more screws just for the little daughter board. So let's try something else. This is a snap fit tester I printed on my resin printer. It's quite satisfying to snap off these supports. But the snap fit doesn't, well, fit. With a little persuasion though, it does snap, so I'll call it a 50% success. Thing is, I'm using a tough resin for these parts, but this sure looks like a brittle fracture to me. I suppose toughness is relative. It is able to handle a good amount of strain, so I'll cut it some slack. Okay, maybe not quite so much strain, but you get the idea. Anyway, I tried printing an alignment jig, which actually got the job done. The thing looks a little worse for wear, but it seems to work okay. So I put it in the new base designs. By also using locating posts for the daughter board, we've reduced the total screw count by 56%. I used a whole bunch of print supports for the bottom side, but they ended up pretty badly warped anyway. This is supposed to be flat, but is clearly not. We'll fix it later in the video. Here's another problem. The non-slip bottom of the dial was made using a rubberized spray, but it isn't exactly hard wearing. So let's try something different. This is a resin printed mold. The idea is to stick a skeleton in a mold and overmold it with silicone. As is typical, the resin prints come out a little warped, so there's a visible gap between the mold halves. But it's okay, we'll just clamp it shut. I mixed about 20 grams of silicone, which is 0.7 ounces. Not the fluid kind of ounces, mind you, because that's obviously a measure of volume. The silicone needs to be degassed in the vacuum chamber, and then injected into the mold using a syringe. Demolding took a bit of effort, and there was a very real chance that I'd stab myself with the screwdriver. But we got there eventually. It's pretty cool how even the smallest features are replicated in the silicone. However, the resin printed skeleton doesn't help with the stiffness too much. But as intended, the silicone is non-slip to the max. As a bonus, I've got a cool casting of the syringe. The next thing that needs to be fixed is the power switch. It's all grey, so I can't tell if the thing's on or off. First, let's see how the pros do it. I took apart my Logitech trackball to get to this slidey boy, and it looks like they're using some kind of sticker, which is actually a really good idea. The raised lip also protects the sticker from wear and reduces the sliding friction. Custom stickers are gonna take a while, so in the meantime, I'm gonna try some enamel paint. I've updated the design to also have a raised lip, and I'm painstakingly painting this under the microscope. The result looks alright, from a distance. But the painting is seriously labor intensive. Luckily, the stickers arrived. They're just simple paper stickers and clearly not of the top quality. They just aren't cut very well and they tear easily. I'm sticking them onto these new prints and they fit surprisingly well. But applying these stickers isn't exactly easy either. There must be a better way to do this. Meet the better way. The Bamboo Lab H2D, which Bamboo Lab kindly sent me. It has 2 nozzles, which will come in handy in a bit. Bamboo Lab also sent me their AMS2 Pro and their AMS HT, which means I can now print this 3-color part without breaking a sweat. My previous printer was about 5 years old, and it feels like I've emerged from a cave straight into the space age. Here's the H2D printing in real time, with the default settings, and it almost looks like it's teleporting a little bit. The most surprising thing is, it actually fit first try. That has virtually never happened to me. There's of course still some waste doing a multicolor print, but the same amount of waste would be generated if I printed 597 of these things, which I think is pretty cool. If you find yourself using a tool all the time, it's probably a good tool. By this measure, the H2D is fantastic. I've only had it for a couple of months, and it's already solved so many problems for me. The best part is, I don't think I've even had a single print failure so far. Now, let's get serious. If you have watched the previous video, you know I have an aluminium dial and a polycarbonate dial. I need to add a wooden dial to my collection. But wood is not exactly an engineering material offered by CNC services like PCBWay. So the plan is to do it myself. How hard can it be? I'll start by getting a small and affordable CNC machine. Like this guy. Yeah, just kidding. I got this little toy instead. It's a desktop 3020 CNC router. It has linear guides, lead screws, NEMA 17 stepper motors, a 500 watt DC motor spindle, and no warranty whatsoever. The frame is aluminium, and what's this? The power supply's mounting threads have already been stripped. Not a great start. The limit switch looks alright, but looks can be deceiving. This screw head collides with the bearing block before the switch is triggered. The other side is pretty suspicious too. Why would they use just the bottom screw hole? Well, let's find out. Hidden behind the switch are actually two holes, and one of them is not looking good. I think that's a broken tap in there. Well, I can empathize. Using a dial indicator, I can verify that the bed is not even remotely flat, but at least the axes are pretty square. Overall, it's not pretty, but I can make it work. At least until the y-axis freaking died after a few test cuts. If you can guess what the problem is, you're a genius. This leaves me with no choice. Just kidding, I figured out the problem. This pad under the control board's microcontroller has lifted off, so I patched it up and saved myself 40 grand. Finally, some action. Let's make some walnut chips. This cut is not exactly fast, and it already sounds like it's struggling. But luckily,
if you can play something slowly, you can play it quickly.
I'm pretty sure the spindle is the weakest link in the machine. You can even see the shaft flexing when it chatters. I sense an upgrade on the horizon. Overall, I think it went reasonably well for my first try. I even got some chamfering done. There is some tear out because I used an upcut bit, but it's nothing unexpected. The thing got chewed up a little bit by the chatter, but the diameter looks close enough. But of course, straight walnut isn't gonna cut it for our demanding application. What we need is stabilized wood. The Wikipedia article isn't exactly comprehensive, but the process is dead simple. Dry the wood out using an oven, submerge it in the stabilizing resin, replace the air and things inside the wood with resin, wrap it and bake it until it's cured. Here's what I got. And it looks terrible. Well, if it worked, it should be slightly denser than water, maybe around 1100 kilograms per cubic meter or 1.15 ounces per US fluid ounce. To find out, I dropped it in some water. Not to be a wood half floating kind of guy, but I think the stabilization didn't exactly go to plan. Okay, it took me a while, but I figured it out. I just had to vacuum pump it harder and longer. You're probably looking at stabilized wood right now. It sinks like a rock, so that's a good sign. And it only cost me my vacuum chamber's lid. And a new vacuum pump. Anyway, I cut the block open to check if the resin penetrated fully. But I don't know what I'm looking at, which is not a bad sign. So let's get back to some CNC. I previously used the tape and glue work holding method, which kinda sucks. Behold, my resin printed vacuum work holding jig. I printed this before I received the H2D, and as is typical for resin prints, the thing is crazy warped. I know some people are gonna say that I printed it the wrong way, so I printed it in 3 more orientations. And guess what? They are all warped to the nines. This one, which was printed at 45 degrees, is the worst by far. But it's alright. I'll just stick it in my flat maker. And I'll also do the other side for good measure. Now that it's all flat, I can install the silicone sealing strip to complete the fixture. I rescued this vacuum pump from my old pick-and-place machine. Sadly, it only pumps down to -60 kilopascals, which is about 1.5 feet of mercury. so I called in reinforcements. This pump vibrates like crazy, but can do almost minus 90 kilopascals. Pretty impressive. Put in series, these pumps can do about minus 95 kilopascals. That's 2 foot 4 of mercury. Vacuum pumps together strong. I stuck everything in a box with a PWM controller, and it's ready for its first rodeo. The vacuum area is only a 65mm circle, so at minus 95 kilopascals, this fixture exerts about 315 newtons of downward holding force, which is 71 millikip. If you're one of those eagle-eyed viewers, you might have noticed the spindle looks different now. That's because I've replaced the weakest link in the machine with this chonky guy. It was practically a drop-in replacement. I just had to build a control cabinet around the VFD and throw in a water cooling loop. I don't want to sound too surprised, but it actually worked. The finish isn't great, but this is just the blank that's gonna get stabilized. Problem is, my vacuum chamber's lid is now one big crack initiation site, so I should really stop using it. So I made a new vacuum chamber. We need to keep the blanks fully submerged, so that's what the white 3D print does. The bubbling starts off pretty vigorous, but my chamber has plenty of headroom. It's pretty cool to see all those bubbles streaming out of the pores of the wood. Now, we're just gonna have to wait, so I'll come back in a day or so. It's been a day and all hell's broken loose. I'm no detective, but I'm guessing ABS doesn't like this resin. Well, at least the bubbling has almost stopped. The pieces that aren't fully submerged will no longer be properly stabilized. We've already had 2 escape, so let's release the vacuum before any others decide to make a bid for freedom. The tape marks the resin level, so I would know when it's been fully absorbed. But of course, these 2 pieces decided to start sinking, which meant the resin level fell and rose back up again. Just to be safe, I left it for a couple of days before fishing them out. Curing with the air fryer was the one thing that went smoothly. And this is what we're left with. It looks like regular walnut, but it's noticeably denser. It just needs 2 more operations in the CNC before it becomes a dial. I printed another vacuum fixture, this time using the H2D. It has a TPU ring to absorb tolerances and little notches to lock the blank in position. I'm using a straight fluted end mill to reduce tear out, which seems to be working pretty well. Look at those chips fly. Next is the roundover bit. Yeah, it looks alright. I was a little worried about the roundover, but it blends in pretty well. The machine marks are still visible from the facing operation, but we'll take care of that later. So it's time to machine the other side. Op2 needs a more considered setup, because if I screw this up, the inner and outer surfaces will not be concentric, and I would have brought shame upon my family. So for this, I'm using a self-centering vise. I use a touch probe to find the center position, and rotating the probe 180 degrees between measurements should reduce the error caused by runout. To actually hold the part, I 3D printed some soft jaw blanks, which then get milled to final dimensions in the CNC router. I only realized there wasn't enough clearance in the Z-axis after I completed the setup. But I am glad I didn't crash the machine. It's not a big deal. I'll just redo all the setup without my spoil board. Finally, we get to do some cutting. But apparently, things were still going too smoothly because... Let's see that again. Nice. My first cut in stainless steel. Check out that surface finish. If you can guess what went wrong, I'll be impressed. So, is it finally time? Nah. Finally, we get to do some cutting.
Oh, déjà vu.
That was just the soft jaws. Now we can move on to the main event. And it's finally complete. Isn't it just perfect? No, it's not even close. My CMM tells me that the x-axis is about 0.3mm oversized, which is about 12 thou imperial. The y-axis is nearly a full millimeter off, which is a lot of thou. And the diagonal is completely off the charts at 1.3mm out. With such an abysmal circularity, I couldn't reinvent the wheel even if I had to. A 1.3mm error is absolutely ridiculous, so I rechecked my machine by engraving 4 dots in a rectangle. But everything looks bang on, and the diagonals are equal, which means the machine is still square. I already made a simple backlash eliminator for this machine, so to check if it's still working, I made the machine move back and forth in 50 micron steps. The backlash seems to be maybe 40 microns at zero load, which is pretty decent. I'm not convinced 40 microns of backlash could cause such a huge error, so I wrote a simulator to replicate my real measurements. And I think the backlash needs to be closer to 0.25mm for this to happen. Anyway, it doesn't hurt to throw a little money at the problem, so I upgraded to these closed loop steppers. I also hacked in thrust bearings on both ends to take some load off the motor bearings. These are the new stepper drivers, which required a new controller. The new controller supports backlash compensation, so let's see if it helps. We start from 0, move some distance forward and back. And if it comes back to 0, it means the backlash compensation is working. I would say that's pretty good. I ran the steps per millimeter calibration again, just to be sure. And I actually filmed it this time. Spoilers, everything's still perfect as far as I can measure. With the new motors, the machine can move or crash way faster than before. In fact, the Z-rapids make me pucker a little. I'm cutting some MDF test donuts to see if I've managed to buy myself some accuracy. The donut has a 70mm outer diameter, same as the dial we're actually intending to make. Surprisingly, the inner diameter's almost perfect, and the outer diameter's improved a great deal, and is now within about 0.2mm. For context, 0.2mm looks something like that. We're not quite at the pinnacle of machining accuracy, but we'll have to live with it for now. Okay, let's try walnutting again. The OD looks alright, so let's keep going. My aluminium dial is probably the closest thing I have to a reference, so I'm using it to zero my vise. Looks good. Finally, some decency. I've intentionally made the OD slightly oversized for the next step, which involves the loving touch of some sandpaper, which this surface desperately needs. As you might know, manual sanding is not for me. So I designed this completely novel device that spins the workpiece, making sanding easier. It has a foot pedal which activates the spinny bit. This fixture thing is printed in PLA with TPU for AMS. The TPU helps to ensure a snug fit, so it's all work and no play. As planned, this jig makes light work of the sanding. Just look at that sheen. The walnut's been stabilized, but it still needs to be finished. I'm putting on a few coats of wipe-on polyurethane. And while the finish is curing, let's jump all the way back to fix something you've probably already forgotten about. This resin-printed part that's crazy warped. As you might have guessed, I'm using my flattening machine. This operation doesn't really need to be accurate, so I'm using these bright red 3D printed soft jaws. I'm centering the work coordinates using the part itself, and I printed a feature I used to align the part by eye. Not gonna lie, it's removing much more material than I was expecting. This must be cutting several millimeters deep, but I'm gonna trust the process. Looks mighty flat. Let's assemble ourselves a full scroll dial. I start by gently coaxing the ceramic bearing into the base. The daughter board needs one screw to hold it in place, and the main board fits perfectly in its machined pocket. The FFC is a little finicky to insert, especially if I plan to make a few of these. The battery is stuck down with some double-sided tape and plugged in. The switch slide can be installed in the wrong orientation, which is not exactly poka-yoke. And our silicone overmolded cover goes on with 3 screws. The magnet is attached with a pinch of glue. And even though we have these screw holes, they are actually the backup plan. Plan A is to have the dial press fit onto the bearing. And it worked. Time to see if this thing works for real. I like the sensitivity set to 4 flashes. And it's time to take it out for a spin. It works just as well as my other prototypes, so no complaints there. The walnut does look and feel pretty good, but I'm not sure about the walnut resin look. What do you think? After all this work, I suppose the question is, was it worth it? Well, just look at it. But no,